We designed our ghost, tested and verified our design, and synthesized it. We placed the design onto silicone and routed its connections, and finally, the physical design crystallized onto silicone. But there is still one more step, and this step is the most critical one, because all of this work must fit into a single file, and the name of that single file is Bitstream. This is Axiom Tech, and I am Epoch. In this video, the ghost will awaken on real hardware for the first time. An FPGA fresh from the factory is empty. Every LUT reset, every switch point undefined. The Bitstream is the configuration file that fills this void. Inside it are bits that define what every LUT will do, bits that determine the state of every routing switch, BRAM initial values, clock configuration, CRC verification. This file is the command sequence that tells the FPGA, "You are now the ghost trader." Imagine a music box. Springs, gears, vibrating tines are ready, the main mechanism, but the cylinder is empty. No pins, no sound. Then pins are pressed into the cylinder from a template. Each pin defines a note. The cylinder begins to turn and music comes out. The Bitstream is that template, and the FPGA is that music box. A single command in Vivado. Write Bitstream. Output ghosttrader.bit, 34.2 megabytes. The Ghost's entire architecture, every LUT configuration, every routing decision, every nanosecond of precision, in a single file. The Bitstream file and the FPGA board are ready. Now a bridge is needed between them to load the Bitstream file onto the FPGA board. That bridge is JTAG, Joint Test Action Group, a 4-wire serial interface, the standard method for hardware programming and debugging since the 1990s. TDI, data input. TDO, data output. TCK, clock. TMS, state machine control. These 4 wires will carry the Bitstream from the computer to the FPGA. Interested, JTAG is not fast. But JTAG's job is not speed. It is reliability. Every bit is delivered in the correct sequence, at the correct time. CRC verification runs at the end of every frame. A single error. Programming halts. The error is reported. The process restarts. Think of a delivery system where every parcel is scanned at every checkpoint. Barcode reading, weight check, and address verification. The first priority here is correct delivery, not speed. This is exactly how JTAG works, delivering the Ghost's 34.2 megabytes to the FPGA bit by bit, frame by frame. We open Hardware Manager in Vivado and click Program Device. The progress bar fills. With every 1% of progress, thousands of configuration frames are written to the FPGA. Every LUT's 64-bit table settles into place. Every routing switch takes its state. BRAMs load their initial values, and on screen, Program Verify complete. From this moment, the FPGA is no longer an empty silicon. Every LUT is running the Ghost's logic. Every routing switch is carrying the Ghost's signal paths. Every BRAM is holding the Ghost's order book. No software, no operating system, only silicon and physics. Simulation is over. Real hardware testing begins. A traffic generator produces real Ethernet packets, in fixed protocol format, in real market data structure. These packets enter the Ghost directly over fiber optic, and we wait. We watch the signals on the logic analyzer. Tavalid went high, Taredi responded. Handshake occurred, BRAM write signal triggered, DSP computed risk, TX order fired. Every stage of the pipeline behaving exactly as it did in simulation, on real hardware, in real time. This is acceptable because there are physical PCB traces, connectors, and fiber optic delays involved. Despite all these additional delay factors, it is still several orders of magnitude below any software-based system. The critical measurement on the oscilloscope. The time from the first bit of the incoming packet to the outgoing TX order signal. 193 nanoseconds, 6 nanoseconds more than the 197 nanoseconds in simulation. The fastest software HFT system operates in microseconds. The Ghost operates in nanoseconds. The difference reaches up to 1,000-fold. There is no optimization here. There is a fundamentally different architecture here. Final test. Real historical market data. March 2020. Tens of thousands of ticks per second. The Ghost is processing this data at real-time speed. On real hardware, we monitor every signal in the ILA. Every packet is processed. Every price updated. Every risk computed. The system is operating stably and without issue. 47,293 packets. 0 errors. 193 nanoseconds average latency. 13 nanoseconds jitter. Look at these numbers. The difference between maximum and minimum is 13 nanoseconds. The Ghost runs at the same speed every single time. No deviation, no exception. We started from RTL, simulated, verified, and synthesized. Later we placed, routed, and generated the bitstream, and last of the process we programmed and tested. The Ghost is no longer an idea, a script, and not a simulation. A machine running on real silicon, in real time, with deterministic physics, without an operating system, without a software layer, only electrons and logic. This is Axiom Tech, and I am Epoch. I will see you in reality.